We're now going to formalize some of that guess and check technology and give you a system to ensure that the answer you get always is arrived at systematically if you want to do it that way. First off, we're going to start with this fairly complicated integral here. X cubed square root of x to the 4 plus 5. And we claim it's this. So the nice thing about claiming that there's a solution or a value for an integral is that we can check it really easily. We just differentiate. We don't actually have to find it ourselves, we just have to verify that it's correct. So we're going to check by differentiating. And that just means finding the derivative of 1/6 x to the 4 plus 5 to the 3/2 plus a constant. And it should equal the original integrand. If this is the antiderivative of x cubed square root of stuff, then this should be the derivative of 1/6 everything to the 3/2. Okay, the derivative is straightforward. We take the 3/2 down front. We get x to the 4 plus 5 to the 1/2. The derivative of the constant by itself is 0. Oh, wait, we still have the chain rule. We're going to have 4x cubed multiplying out as well. And if we work through this, we have in the denominator we have 12. In the numerator we have 12. And then we get x cubed square root of x to the 4 plus 5. And that, of course, equals x cubed square root of x to the 4 plus 5. And this equals the original integrand. And if that's the case, we have the correct antiderivative. So this is the antiderivative of this complicated x cubed square root thing. Okay, our next question is, how would we have known that if we had not been given this? How would we have seen what the antiderivative might be? Let's take a look. If we look at the pieces, if we look at that x cubed square root of x to the 4 plus 5, you'll notice that this part here came from the derivative of something to do with this x to the 4. We had a function inside, and then we had its derivative. Derivative of x to the 4 is like x cubed, up to some constants. And so we had this pattern of function inside something else multiplied by its derivative. So we're going to take advantage of that and use that as part of our substitution idea. We're going to do this by example, and we'll just jump right in with the techniques we expect you to use as students as you get more familiar with this substitution approach. Okay. We're going to define a new variable. We're going to call it w, and we're going to let it equal this thing inside the function here, x to the 4th plus 5. Why do we pick that? Again, this is our function, and we're going to get its derivative on the outside. So this is our internal function, and we expect to have something about a derivative coming up later. Speaking of which, we're going to want the derivative of w, which will be 4x cubed. And the most straightforward way, I think, to do these is to break this into pieces. So one little note here. dw is a unit. Treat dw dx as small units of w, small units of x. For those who have heard the term differentials used before, that's one way to think about this. Essentially, it's the ratio or the connection between small changes in w and small changes in x. But it means we can actually rearrange these. So what we're going to do is we're going to bring the dx up, and we're going to bring the 4x cubed down so that we get 1 over 4x cubed dw is equal to the dx that we bring up to the other side. Now, what's the point of doing that? Well, if we have that substitution, what that lets us do is rewrite the dx in our original integral, little units of x. We're going to trade those for little units of w, but it's not a one-to-one trade because the relationship between w and x is complicated. So this will be the relationship between small changes in x and small changes in w. It'll be scaled by that 1/4 over x cubed. What does this do for us? Well, we rewrite the original integral in terms of w. And of dw, equally important. The integral of x cubed, square root of x to the fourth plus 5 dx can be translated. The x cubed we can't do much with. That's just there. But the square root part, x to the fourth plus 5, is exactly what we said w was. And the dx is exactly what we said here. It'll be 1 over 4 x cubed dw. So this whole term here is our original dx. And what do we see when we do that substitution? We get a great cancellation. This is where we're getting that benefit of the chain rule. We think this x cubed came from the derivative of x to the fourth, and by making our substitution involve x to the fourth, we get to cancel out those spurious x cubed terms. Now what's the real benefit when we tidy? We have a 1/4 out front, keep the same font color. We have a 1/4 out front, the integral of the square root of w, dw. Well, that is way simpler than the integral that we started with. In fact, we know how to do that because it's w's and w's. We're going to get w to the 3/2 over 3/2 plus a constant. Now we can actually do that integration. So what we did with the substitution was trade a complicated integral for a much simpler one, and the only penalty we need to pay is to convert it back into the original values, which were x values. The original integral had x's everywhere. We have w's. We should go back to the original. We have 1/4 and 3/2. Let's do the constants. That'll be 2 over 12. And then the w to the 3/2 is our x to the fourth plus 5 to the 3/2. The plus c doesn't change. And actually, that's just 1/6. And if we look back a page, that's exactly what the correct answer is. 1/6 x to the 4 plus 5 to the 3/2 plus a constant. So this has given us a method, a strategy, a systematic approach to find the antiderivative of a complicated integral like this.